Now let us consider another example on Taguchi analysis. Okay, in this example, we will consider the mix design for Taguchi design. Okay, now what is mixed design? Initially, in the first example, what we have taken, the number of factors, all the factors are having equal number of levels. But if in the case some of the factors are having different levels from other factors, then what we have to do? So in that case, what we have to choose? We have to consider the mix design. Okay, so in this case, we are going to select a problem which is having different levels for different factors. Okay, so let us start again go to Minitab, click on the Minitab. Now you will see the initial interface for Minitab. Go to stat, then go to DOE. Okay, then go to Taguchi, create Taguchi design. Okay, now here you will see that the number of factors are 4. We are considering 4 different factors. Okay, and here, as you know, that we are having a factor which is having only 2 levels, and 3 different factors out of 4 are having 3 different levels. So this is not a simple problem, this is a mixed design type of problem. So this can be considered as a mixed level design. So click on or select this mixed level design. Okay, now display available designs. Okay, what now what you have to do here? Now we are not selecting the single level system, we are selecting what? Mix 2 3 levels. Okay, or as we are having 2 to 3 levels only, not 2 to 4 levels, so we are selecting this mix 2 to 3 levels. Okay, now this is one of the factor is having 2 levels, and 1 to 7, here in our case we are having 3 other factors which are having 3 levels. So initially we are selecting this L18. Okay, so click on this. Okay, okay, now this is the design. What we have to do? We have to select L18. Here you will see that this is the L18 array. Okay, here one of the factor is having 2 levels and 3 of the factors are having 3 levels. So select this L18. Okay, now click on L18. Okay, now what you have to do? Again you have to introduce the factors. Okay, we are considering the problem of a honeycomb core sandwich panel. Okay, which whose different property different on different factors. So we are considering 4 different factors for this type of analysis. Okay, so initially what we are having, we are having a factor. First factor is the we can use here, first factor is the height of the core. Okay, oh sorry, core cell size. First factor is core cell size of honeycomb core. So we can put the coding here in the form of cell size. Okay, and the cell sizes are 3.2 and 4.8 mm. Okay, this factor is having only 2 levels. Now then the second factor, again go here, and then you will see that this is the thickness of what? Face sheet. Thickness of a face sheet. In a sandwich structure, 2 different things are there. One is a core, and on that core at the top and the bottom there are 2 thin sheets. Okay, which are called as the face sheet. So the second factor is face sheet thickness, FST. Here you will see that we are considering 3 different levels for this face sheet, that is 0.4, 0.6 and 0.8. Okay, so 0.4 is the first thickness, 0.6 is the second thickness, and 0.8 is the third thickness. Then the third factor is core height. Okay, and we have considered the core height as 8 mm, 10 mm and 12.7, that is the half inch. Okay, you can confirm this from here also, 8 mm, 10 mm and 12.7 mm. Okay, now the fourth factor is the panel width means के the specimen which we are going to test, it has 3 different widths. Different specimens are being used which have different widths, and this has been considered 40, 45 mm and 50 mm. Okay, now these are the 4 different factors. These are different levels. Here you will see that the first factor is having only 2 levels and rest of the factors are having 3 levels each. So this is considered as a mixed level design problem for Taguchi analysis. Okay, now click on, as we have entered the factors and levels, then we have to proceed further. Okay, now click on go. Okay, then again click on OK. Now you will see that we are having a L18 array. Here you will see that one factor is having 2 levels and 3 factors are having 3 levels each. Okay, number of factors are 4, and now you will see that we are having the total number of experiment as 18. Okay, now in the Excel sheet here you will see that these are the different combinations or the different runs. Okay, now we have to perform the total 18 experiment. Okay, here in this case we again have considered the 2 different levels. Okay, 2 different levels. One level is of what? Larger is better type, and the another level is of smaller is the better type. Okay, then again we will perform a Taguchi analysis for the combination of those 2 levels. Okay, so let us enter the values of the different responses obtained after performing the experiments on all these 18 experiments. Okay, now we will copy the values from the table as we have already performed the experiments. Okay, so we are having the values for D, that is bending stiffness. Okay, this is our first response. Please take care that you have to enter from the top. Sometimes there could be possibility that you have entered the values at a wrong place. Okay, in that case your results will be wrong. Okay, so from here we are entering the values of different responses. Okay, so these are the values of different responses for these different types of runs. Okay, so this parameter or this response is always a larger is better type of option, as we always require higher bending stiffness so that the sheet or the composite material will not bend. Okay, now the second option is, or the second response is stress. Okay, plain stress. This is what? Stress. We will represent this as S. Okay, now again put the different values of different responses for all these 18 experiments. Okay, now as we have entered the values of responses for all these 18 runs, now we will perform the Taguchi analysis. The first response, that is D, is of what type? Larger is the better type, and the second response is of what? Smaller is the better type. Okay, so let us perform the Taguchi analysis on both these responses one by one. Initially we will perform the Taguchi analysis for bending stiffness, that is D. So again move to stat, then select DOE, then again Taguchi, then analyze Taguchi design. Okay, initially what we are selecting? We are selecting D. Okay, then select. Now what type of graphs we are looking for? Signal to noise and means. No interactions has been considered here. Then again signal to noise, then terms, you don't have to change anything here. Options, now as we always require that stiffness should be maximum, so what we have selected, larger is the better option. Okay, okay, now click here. Okay, okay, so this is the S by N graph. Okay, this is the graph for means, and again here we have got the response tables for what? Signal to noise and means ratio. Okay, so here in this response table you will see that co-write is the most significant factor. Okay, as it is having a rank 1. Okay, now from the graph S by N plot, okay, what we can have, you can also fetch this graph again from here, main effect plots for S by N ratio. Okay, so here you will see that the 4 different conditions, okay, for 4 different factors, and we can have a combination on which the best stiffness can be fetched. Okay, so here you will see that these two values are on the same level, means ke core cell size is not having much effect on what? Stiffness. Okay, as these two values are equal. Okay, so we can say that core cell size is not a significant factor which affects the bending stiffness property of a sandwich panel. Then phase sheet thickness, you will see that there is a larger gap here in the top and the bottom point, so this is a significant factor. And at which phase sheet thickness you are having the maximum bending stiffness, that is at 0.8 mm. If the thickness of phase sheet is 0.8 mm, we can have the highest value of bending stiffness. Then core height is, you will see that here is also a significant factor. Okay, now at what core height you will be having a highest stiffness? 12.7 mm. Then at what panel width? At 50 mm. So the best combination is what? 3.2 or 4.8, any
can be taken.
Cell size can be considered. Yes. But phase sheet thickness should be at 0.8 mm, 12.7 mm and 5 mm. So combination is, we can consider this as 3.2. Now if the cost is different, then select the cheapest core cell size material. Okay, so depending on different factors, to select the best material in the form of core cell size, and then phase sheet thickness should be 0.8 and CH is 12.7 and width should be 15. So we have a combination. We can consider this as 3.2 mm, 0.8 mm, 12.7 and 50 mm combination for having the better optimum values of T. Okay, now again let us move to DOE. Now what we are going to do, we are having the Taguchi analysis for the stiffness. Okay, oh sorry, stress. Stiffness has already been considered. Now what we are going to have, the Taguchi analysis for the stress. Okay, then select it. Okay, now as we always require what, the minimum stresses should be there in the materials. Okay, so smaller is the better option has been selected. Okay, now click on OK, then click on OK. Okay, now this is again all the different values are there. Again here you will see that this is the S by N plot. Okay, now the different values can be considered here. Again you will see that 3.2 is a little higher as compared to 4.8 mm. So 3.2 can be selected here. Also you will see that again CS, core cell size, is not a significant factor for the stresses. Then phase sheet thickness, again this is the dominating factor. Phase sheet thickness is the dominating factor for determining the stresses. Okay, so for having minimum stresses, the phase sheet thickness should be 0.8 mm. Then core height, again it is 12.7 mm, and then it is what, 50. You will see that the panel width is also not a significant factor. It is having a nominal effect on the stresses value, but still 50 is the better option. Okay, so again the findings are 3.2 mm, 0.8 mm, 12.7 mm and 50 mm, similar to that of the bending stiffness. So for having a better stiffness and stress values, the optimum combination is 3.2 mm, then 12.8 mm phase sheet thickness, core height should be 12.7 mm and panel width should be 50 mm. So now let us check, does these values or exist in the orthogonal array, or this combination is not available in the orthogonal array. Okay, if this combination is available in the orthogonal array, then we don't have to perform any experiment. We have to check is our findings correct. Okay, if this combination, that is 3.2, 0.8, 12.7 and 50 is not there in orthogonal array, then what we have to do, we have to run an experiment with this combination, and then we have to check whether the values of bending stiffness is maximum for that and the value of stress is minimum for that combination. Okay, so let us check whether we are having any combination. So let us go to 3.2 mm. Okay, now 0.8, 12.7, but 3.28, 50, 3.2, 0.88, 45, 3.26. So you will see that there is no such combination available here in the orthogonal array. So now what we have to do, we have to perform a separate experiment. Apart from these 18 runs, we have to perform an experiment with the combination of our optimum values. Okay, and after that we have performed the experiment. Okay, and we got a optimum values with that combination. Okay, so let us check. I will show you that whether we have got the values better in that case or not. So this is the entire experiment. These are the different calculation or the S by N ratio graphs for our findings, similar to that of many time. These values have been considered from the graphs, and the response tables has been taken from the Minitab, the previous analysis. Okay, now you will see that these values are not available in the orthogonal array. Okay, so again the finite element analysis has been performed, and with the combination which we have achieved through GRA and Taguchi, and you will see here that the values obtained with that combination are better than that of the values available in the orthogonal array. So we can say that this type of analysis can be used for having the better optimum values. Okay, now also one more thing you can check here is that if you are going to perform an experiment in which one of the responses of larger the better is type and one of the responses smaller the better than, or smaller is better than type, then what you have to do, if you have to consider both the responses simultaneously, then there is a catch here. Okay, what you have to do, you have to make the both the responses of same type. Either both the responses should be of a larger the better type or the smaller the better type. So what you will do, because you are having the two different types of responses here, and then find out the reciprocal of any of one of the responses. Of all the values of the responses, find out the reciprocal. Now if you will use the reciprocal, then if larger the better type of problems has been considered, then their reciprocal will give you the values which can be used for Taguchi analysis of a smaller the better type. Similarly, if you are going to convert your smaller the better type of option into larger the better type of option, then again find out the values of the responses of the smaller the better type. Okay, and then if you will perform the Taguchi analysis, you will get the results equal to that of the larger the better type. Okay, so if you want to change the type of your response, then find out the reciprocal and then make the Taguchi analysis. So this is the main catch. Okay, in the Taguchi analysis, if you are considering multi objectives or multi responses simultaneously at a single instant of time. Okay, so this is what the Taguchi analysis.